Conservation of mechanical energy. This is a big deal. This is a very powerful problem-solving technique. So let's get started on it. Let's kind of go back to the last situation. Here's our plane right here, and here's our ramp, our platform. Here's a little sleeping cat or something, I don't know. Pick whatever annoys you the most. It can be me. I'm taking a nap, all right? And then I'm allergic to cats, okay? My eyes explode. They're indifferent to me, and I'm offended by that. So I need unconditional love, and that's why I like dogs. All right, so I do. I have 2 of them.
That's cool.
All right, and they're really dumb, but they're cute. Okay, so let's put our crate up here. And it has a certain mass. And then let's say, okay, it's hovering over the cat, and it's about, the Looney Tunes gravity is about to strike, and boom, it strikes. All right, so this thing has gravity pulling it down, and it has gravitational potential energy. It started up here. So we'll say U initial is equal to mg y initial. Does that make sense? Like this is y initial up here. We'll make the ground the origin. So here's the y direction, and here's the x direction. But the x direction is irrelevant in this problem. Okay. Well, let's say you get just above the cat, maybe a meter or so above the cat. The cat sees what's coming, and it skedaddles. It's safe. I'm not going to kill any cats, even in my imagination. I just can't do it. But we still got the force of gravity acting on this thing, and gravity. And so we'll say, look, here's y initial up here. Here's y final right here. Okay, obviously, gravity did some positive work, didn't it? We have our displacement, our delta y is like this. Our gravity is like this. It did positive work. Now let's go back and remember something we derived a few days ago called the work-energy theorem. The work done by the net force is equal to the change in kinetic energy of our object. So if there's a net force acting on your object, then that net force, if that net force is doing work, then you're changing the kinetic energy of your system. The system here is the crate. Well, look, I've got a force acting on my, acting on here. And so the work done it's going to be by gravity. And so let's figure out how much work that is. This is, well, let's start off. F dot dr. Now, I think you can agree with me. Gravity here is the net force. So this is going to be gravity. Gravity is the net force, and that's going to be equal to the change in kinetic energy, which is K final minus K initial. Am I still on screen? Yeah. Okay. Well, what's the force? The force is mg in the negative j hat direction, dotted with dy in the j hat direction. And we're going to go from y initial to y final. This is just what I did last time. But what do I get here? I get negative mgy from y initial to y final. And this is equal to negative mg y final minus negative mg y initial. God, this is really messy. So let's make this minus, minus a negative is just adding a, what was that? Adding a positive. And so this is going to be equal to mgy initial plus, minus mgy final. It's a minus right here. Or, hey, here's another way of looking at it. I'm sorry, I'm gonna change this a little bit. I'm gonna put this right here is, if I pull a negative out, let me do it this way. Pull the negative out. Then you have mgy final minus mgy initial. Correct? But if I pull the negative out, which I should have done in the first place, what is this? What is mgy? Well, mgy final, that's my final potential energy, correct? And this is my need a better eraser too. This is U initial. Well, this is U final minus U initial. What is that? That's delta U. So this is equal to negative delta U. That is the work done by gravity as this thing falls down is equal to the loss of my gravitational potential energy. And doesn't it make sense if I'm holding a bowling ball over your head? The bowling ball has gravitational potential energy. If I release it, it goes down. My gravitational potential energy becomes less and less and less and less. I'm losing gravity. In other words, I have a negative change in gravitational potential energy. But since the force of gravity is my net force and it's doing work, that work results in a change in kinetic energy. Okay? Now, I want you to really focus right now. This is a really important idea. And it's really quite simple. It's very, if you can get it. Okay? When I drop an object, it gains kinetic energy. But the amount of kinetic energy it gains is equal to the amount of potential energy it loses. Does that make sense? Because the energy has to come from somewhere. And so, now watch this. This is, I'm going to add delta U to both sides. And when I do that, I get delta K plus delta U equals what? 0. So what's happening here is that if gravity is your net force doing work, if you add up the change in kinetic energy plus the change in potential energy, you get 0. There's no change overall. This means something is not changing. Something is being conserved. And it's the energy of the system, if you include kinetic energy and potential energy together, that sum is not changing as the object falls. So here's what we're going to do. Well, actually, let me take this expression, delta K plus delta U equals 0. And what I'm going to do is I'm just going to break these apart. K final minus K initial, that's delta K, plus U final minus U initial equals 0. I'm going to put all the final all the initial stuff on the other side. I'm going to add the initial kinetic energy to both sides of the equation and the initial potential energy to both sides of the equation. Okay? Now here we're using pure mathematics, you guys, to derive these ideas, but don't think of these as just symbols. Think of what they mean, what they stand for. This is how much energy the object has at the end, just before it hits the cat. And this is how much potential energy it has at the end. It will be equal to the amount of kinetic energy it started with plus the potential energy it started with. Okay? Now, this is such a big idea that we have a symbol and we have a name for the sum of kinetic energy and potential energy. And we call that sum mechanical energy. K plus U. By definition, we're going to call it E. From now on, when you see E, that's going to stand for mechanical energy, not just energy in general. I mean, there's other forms of energy, right? You got thermal energy, internal energy, and all that kind of stuff. But right now, for what we're doing in this chapter, E is going to represent mechanical energy. And by definition, mechanical energy is equal to the sum of kinetic plus potential. Now, this potential energy can be gravity, gravitational potential, or elastic. And I haven't really talked about elastic yet, and I'm not sure I'm going to have time to today. This gravitational potential energy is the energy associated with your position in a gravity field. Elastic potential energy is the potential energy stored in a stretched spring or a compressed spring. Now, I'm going to cheat a little bit. I'm not going to derive it as thoroughly as I did gravitational potential energy because we already did it a little bit. Remember, we said that the work done by a spring is equal to 1/2 kx squared. Okay, we're going to say that the elastic potential energy of a spring is equal to 1/2 times the spring constant times the position from the equilibrium position squared. And remember, you have to understand the assumptions of each equation. This is assuming that your origin is where the where the spring is in equilibrium. There's no energy stored in the spring. That is when x is equal to 0. Okay, this is the first great conservation law in physics that you're going to learn. The conservation, this is called conservation of mechanical energy. Okay. And if I call this E, then what I can say is E initial equals E final. Okay, it's a pretty simple little equation, huh? Now, mechanical energy is conserved. In other words, the energy I started with is going to be equal to the mechanical energy I end up with if and only if the only forces doing work are gravity and springs. So, when you do a problem, when you work a problem, and you say, hey, the only force doing work here is gravity, like when I'm dropping the crate. And you look at the forces involved. Hey, the only force doing any work here is gravity. You can start with this equation. I want you to start with this equation. And then it just becomes an accounting job. Like you have to account for the energy. Okay, initially, where is my mechanical energy? Does it have potential energy? Yes. Put that in there. Put in mgy. Does it have kinetic energy? Put in 1/2 mv squared. Does it have elastic potential energy? Put in 1/2 kx squared. Equals whatever it has at the end. And then you just solve the problem. Now I'm pretty much out of time, but if you look at the examples that I assigned for you to do, they all involve balancing the mechanical energy. All of these things. Now, by the way, if springs or gravity aren't the only forces doing work, what if friction is doing work? If friction is doing work, your mechanical energy is going to change. Usually it's going to get less. Because usually friction, not always, but friction takes energy out of the system. If there's an applied force, somebody from the outside world is pushing on you, that's going to change your mechanical energy. Because your mechanical energy is defined to be the sum of your kinetic and potential. If gravity and springs are doing work, all they're doing is pouring energy from one way of storing it into another way of storing it. This is storing it in a gravity field. This is storing the energy in your motion. All you're doing, think of a pendulum swinging back and forth where there's no friction in a pretend world. Then all we're doing is transferring energy back and forth from these two, but the sum total never changes. But if there is friction, if there are resistive forces, if there are applied forces, then our mechanical energy will change, and we'll deal with that situation. In the next lecture, you're going to get the ultimate energy equation that will apply for every problem that you're ever going to use energy in. And it's not even in the book, unfortunately. All right, that's it for today.